So yeah, in this series of lectures, I will talk about Donaldson-Thomas invariants, flow trees, and log Gromov Witten invariants. Here is a more detailed plan of the lectures. So today, for the first talks of the morning, I will present a general overview of Donaldson-Thomas theory and of word crossing. And the art of the lectures will really be on Tuesday and Thursday. On Tuesday, I will talk about the flow tree formula for quiver Donaldson-Thomas invariants. And on Thursday, I will talk about the correspondence between this quiver Donaldson-Thomas invariants and logarithmic Gromov Witten invariants. So here we'll make some contact with a lecture series of Pierrick Bousseau, which is around logarithmic Gromov Witten theory. And on Friday, it will be a more speculative lecture around so-called holomorphic Floer theory. Okay, so the goal of today is to give some overview of Donaldson-Thomas theory. And in many ways, it might be overkill. So in the next lecture, I will focus on quiver Donaldson-Thomas theory, which in many ways it's an almost elementary topic. But today, I want to present the more general theory and make contact with geometric examples, which should be viewed as a context and motivations for what we will do later. And so in particular, I will work in more generalities than necessary, and I will not be fully precise. Starting on Tuesday, Thursday, I will be fully precise. And correspondingly, today there will be no original material. Original results will be presented on Tuesday and Thursday. Okay. So the goal of these two lectures today is essentially to explain the meaning of what is on this slide. So Donaldson-Thomas invariants are supposed to be numbers, actually some integers, which are counts, they are virtual counts of stable objects in Calabi-Yau categories of dimension 3. And so as a kind of a general introduction, I will need to say something about what kind of categories we are looking at, what is the role of this Calabi-Yau condition, what stable means, and what is dimension 3 about, and what is virtual about this count. So this thing will take us most of the 2 hours today. But at the end of the day, we'll get some numbers, these Donaldson-Thomas invariants. And these numbers, you should really think about them as being part of enumerative geometry. They are counting things. They are counting stable objects. But what stable means can vary. And so there will be a word crossing story where you change what you mean by being stable. And then your stable object will change. And so these counts, these numbers will also change. And there will be a word crossing story about how do these numbers change. And I hope to arrive at this point at the end of today. So what kind of categories are we looking at? So we are supposed to be talking about count of objects in some categories. So all the categories in these lectures will be linear over the field of complex numbers. So you have objects, and morphisms between objects are complex vector spaces, and composition is given by complex linear maps. And I will always consider C a triangulated category, so I will not recall the full definition. You should think about it as something looking like a category of complexes, of chain complexes. In particular, there is a shift operation. So you can send an object E to its object E shifted by 1, denoted by this E bracket 1, which if you think of some kind of complex, is shifting the degree of the complex. And I will always use this notation, xi of EF will be the vector space of a morphism from E to F shifted by I. And so the kind of my first example you should keep in mind, especially if you come from algebra representation theory, if you have a C algebra, you can look to the abelian category of module over this algebra, and then you can look at the bounded derived category of this abelian category. It will be an example of the categories we are considering. And in this context, if, for example, E and F are complexes consisting of a single non-zero term in your category of A modules, these X groups are the usual X groups from modules over an algebra. From a geometric point of view, we'll mainly think about the following example. If X is a scheme over C, then you might consider the abelian category of current sheaves on X, and then consider its bounded derived category. It will also be an example of triangulated category over C. And you should think about it as being an analog of the previous example. If X is affine, if it's spec of commutative algebra A, then this category is the same thing as the derived category of modules of A. And for various claims during these lectures, you will need to impose some conditions on this category. So if you think about a geometric context, if you have a scheme X, maybe you don't want to work with arbitrary X, but you want your X to be nice. For example, you might want X to be smooth, and you might want X to be proper. Let's say compact for the complex analytic topology. And there is a categorical way to express these notions. So often I will assume this category and smooth and proper. So I will not recall the full definition, but you should think about it as meaning that it looks like the derived category of sheaves on the smooth and proper algebraic variety. And for us, at this point, the most important condition is a properness. So in algebraic geometry, the key aspect of properness is that it guarantees that coherent cohomology groups are finite dimensional. And correspondingly, in a proper category, you see a finiteness statement that if you look at the direct sum over I of the xi EF for any two object EF, this thing is a complex vector space, and this thing is finite dimensional. So in particular, there is non-zero only for finitely many I, and all of these X groups are finite dimensional. So some examples of these very nice categories are, for example, the derived category of current sheaves on X, where X is a smooth and proper algebraic variety over C. And maybe you might want to allow non-compact variety X. And what you can do is to consider what I denote by dBz of co-X. If X is a smooth variety of a complex numbers, but not necessarily proper. But if you have a proper subset, a proper subvariety Z inside X, you might consider sheaves or complexes of sheaf E in the derived category whose cohomology are set theoretically supported on Z. They are kind of live on Z, essentially. And then this category will be, again, an example of a smooth and proper category. Here is another example, which is not coming from directly from algebraic geometry, but rather from a representation theory, and which will be a key example both for today and for the later lectures. You can start with a combinatorial object with a quiver Q. So it is simply a finite oriented graph. So it consists of finitely many vertices, and for every pair of vertices, finitely many arrows. So here I've drawn a random example of a quiver. And once you have a quiver, you can naturally construct out of it an associative algebra called the path algebra of the quiver that I'm denoting by CQ. And a basis of this algebra as a vector space is given by path in the quiver, where a path is a sequence, a finite sequence of arrows that you can naturally compose. And if you have two such a paths, you can define their product if by a concatenation. So if you have two paths, and if the endpoint of one path is equal to the start point of the other path, you can concatenate them, put them together to get a new path. And if the end and start points of the path do not agree, you just define the product as being 0. Okay, so there's a natural way to extract an associative algebra from this picture. And then once you have this associative algebra, you can consider modules over this associative algebra. And a module over this algebra is the same thing as a quiver representation. So you might think about the quiver representation in an algebraic way as a module over this algebra. Or in more concrete terms, you can check that this data is equivalent to the data of a complex vector space for each vertex of the quiver. So you think of each vertex of the quiver as being decorated by a vector space, complex vector space sitting over this vertex. And then for every arrow in the quiver, you have the data of a linear map between the vector space sitting at the initial point of the arrow and towards the vector space sitting at the end point of the arrow. Okay, so the quiver representation is just a decoration of this quiver by vector space and linear maps. And then you can consider the category of such representation. So they form an abelian category because they are just categories of modules over an associative algebra. And you can look at the bounded derived category, so roughly bounded chain complexes of these representations. You will get a big category. And if you want to have this kind of properness condition, I need to put some kind of finite dimensionality restriction. So if you have this kind of complex of representations, you can look to the cohomology groups of this complex. You will get a bunch of vector spaces. And I want to impose a condition that the total dimension of these vector spaces is finite. So roughly, you should think that in this representation, all the vector spaces are finite dimensional. And in addition, complexes are also have some finiteness property. Yes?
Do you allow edge loops?
And I think I allow edge loops.
No edge loops.
I think I allow edge loops.
Still is proper.
And I think because I impose this kind of extra condition, I think it guarantees that. Yeah, so if I drop these conditions, then things like loops or cycle will create problems. But I just restrict to something which has like a nice finiteness condition. Yeah, that's right. You can take that as a characterization. Yeah. Yeah, Actually, maybe in a few slides there will be an example containing loops, and I would make a comment about that. Okay, so what were on the previous slides were the two main examples you should keep in mind for now. Either this thing coming from sheaves on smooth proper varieties, or things coming from these quiver representations. Now I want to say something about the Calabi-Yau condition. So maybe I should start by the example before the definition. So in algebraic geometry, there is a classical notion of a Calabi-Yau algebraic variety. It's an algebraic variety which has trivial canonical line bundle. So if X is my variety, let's say smooth and proper, then I have the canonical line bundle, which is a top exterior power of the cotangent bundle. It's always a line bundle on your algebraic variety. And you might impose a condition that this line bundle is trivial. And in maybe more explicit term, if you think about what is a trivialization of your canonical line bundle, it is a top degree algebraic form. So if you want, it is a holomorphic or algebraic volume form on X. And so what is special about Calabi-Yau varieties is for them, the third duality for covariant cohomology of sheaves takes a very simple form. So in general, on any X, smooth and proper, third duality is telling us that this group xi of EF, so which is a finite dimensional vector space by properness assumption, is naturally isomorphic to the dual of xd minus I, where d is the dimension of X, between F and E times the canonical line bundle. And so if the canonical line bundle is trivial, you simply get xd minus E, F comma E. So in the Calabi-Yau situation, you have this natural duality between xi of EF and X and the dual of xd minus I Fe. And the observation is that this property is essentially a categorical notion. And so you can put it in a general definition which no longer refers to the algebraic variety, but only refers to the category. You might say that your smooth and proper triangulated category C is Calabi-Yau of dimension D if there is a version of third duality taking this particularly simple form. So if there exist natural isomorphisms between xi of EF and the dual of xd minus I Fe for every object ENF. And I will not here specify the full definition. You want these isomorphisms to be like functorial in ENF. You want to be like to satisfy natural compatibility conditions with respect to ENF. So the first main example to keep in mind is the one I've just mentioned, covariant sheaves on the smooth and proper Calabi-Yau variety. But there are other examples which have some quite different origin. For example, from a symplectic geometry, there are categories called Fukaya categories, which will have this property. So if Y omega is a compact symplectic manifold, so Y now is a real compact like smooth manifold of real dimension even equal to 2 times D. And if omega is a symplectic form, so a closed non-degenerate 2 form on Y, then in symplectic geometry, there's an object you can attach to this data, which is called the Fukaya category of this symplectic manifold. And actually, if I want this category to be of the same kind of the categories I've been talking until now, if you want it to be Z-graded, I also need to impose some kind of Calabi-Yau type condition. I want the first chain class of Y to be equal to 0. And I will not give any details about the construction of this category. I will just give these pictures. And the only thing I want to mention is where the Calabi-Yau condition come from. And another reason I'm mentioning this example, it will serve as some kind of motivations for some later discussion. So roughly, objects in this category are supposed to be related to Lagrangian submanifolds of Y. So if you have Y a symplectic manifold, a Lagrangian submanifold L in Y is, so it's a submanifold. And first of all, it should be isotropic, meaning if you take the symplectic form omega, and if you restrict it to L, you should get 0. And in addition, this submanifold should be of maximal dimension. So if you are isotropic, you have of dimension at most half the dimension, so of dimension at most D. And so for Lagrangian, you want this dimension to be exactly D. So L is half-dimensional inside Y. Okay, so these half-dimensional objects, these Lagrangian submanifolds, are the objects of your category. And then morphisms in your category are related to count of holomorphic disks with boundaries on these Lagrangian submanifolds. And so here, the only thing I want to mention is that when you count these disks, you look at this kind of picture. So this thing is supposed to be the picture of a disk. And on the boundary of the disk, I've divided the boundary in some number of intervals. And you should think of each of these intervals as lying on some Lagrangian submanifold of Y. And you use this kind of picture to define things like a product or higher product in your category. And the key point is that this is a picture as a kind of cyclic symmetry corresponding to the fact that you can rotate the boundary of this disk. And at the end of the day, this cyclic symmetry is responsible for a Calabi-Yau property of this Fukaya category. If you want to have some maybe more concrete or explicit example of where this Calabi-Yau property come from, you can think of a Lagrangian submanifold L, and let's assume it's oriented. Then under nice conditions, you can check that the xi of LL in this Fukaya category reduces to something very simple, simply the cohomology of L to hi of L. And in this case, the Calabi-Yau property of this complicated Fukaya category reduces to something very simple. It reduces to Poincaré duality for this Lagrangian submanifold. Okay, so in the algebraic geometry context of sheaves, this Calabi-Yau condition is related to some third duality. And here in this Fukaya category context, if you look to what happens on a single Lagrangian, it's very much related to a Poincaré duality on this Lagrangian. So what about the quiver examples? So if Q is a quiver, I described before how to attach to it this derived category of quiver representations, which are finite dimensional. And you might ask if this category is an example of Calabi-Yau category, and in general is not the case. So actually, the category of quiver representations is remarkably simple. Let's assume for simplicity your quiver has no loops or oriented cycles. Then it's easy to check that in this category there will be, in the category of quiver representations, there will be x1, but there will be no x2 or higher x. So it's a category of homological dimension 1. And so in general, it will not have any Calabi-Yau properties. Nevertheless, there is a way starting from a quiver to cook up a category which will have a Calabi-Yau properties and which will be important to fit the quiver story into this broader Calabi-Yau context. And so to do that, you can start with a quiver, or more generally with a quiver with potential. So what I mean by W is a potential for the quiver. And by a definition, a potential for a quiver, it's a formal linear combination of oriented cycles inside the quiver. So if in your quiver, if there is no oriented cycles, so no sequences of arrows forming an oriented cycle, then W would just be 0. But if there are oriented cycles, you can take formal linear combinations of these cycles and take that as your W. It's an extra data you are free to choose if there are cycles. And starting from this query with potential, there is a way to cook up a category that I will denote by CQW, which will be an example of Calabi-Yau category of dimension which happens to be equal to 3. And what this category is will be some category of finite dimensional DG modules over what I denote by G, which is a so-called DG Ginzburg algebra. So I'm describing here what it is. So maybe this slide can look complicated, but you should think about it as being really simple. If you think of quiver representations, there are some x1, which have to do with arrows. And if you want to have a Calabi-Yau 3 condition, so if you think about what does it mean to be Calabi-Yau of dimension 3, it means that x2 should be dual of x1. So if you have non-zero x1, you also want non-zero x2. So to get something Calabi-Yau 3, you would just put some x2 by hand. And similarly, you want x3 to be dual to x0, and so you will put the x3 by hand. And the way to add this x group by hand is to consider a bigger quiver, Q tilde, which is really a graded quiver. And the way we get Q tilde, you first start with Q, your original quiver, and you view the original arrows A as being in degree 0. And if you think about quiver representations, you will see these arrows are related to x1. And so to get x2, you will add arrows. So you will add for every arrow A in your original quiver a new arrow A star in your new quiver going in the opposite direction. And you will assign a degree 1 to this new arrow. And now to get the x3, you need to add this Li for every vertex. You will add a loop at the vertex I, and you will put this loop in degree 2. So this loop will be necessary to get some x3, which will be dual to the x0. So you think about this quiver as being some graded quiver. There is some grading attached to the arrows. And then you can consider the corresponding path algebra of this quiver. It will be a naturally graded algebra. And then you put a differential on this graded algebra, which is given by this formula. So if you have one of the original arrows of your quiver A, you say d of A is 0. If you have one of these new arrow d A star, you decide that d of A star is a partial derivative of your potential W with respect to A. And if you have one of these new loop Li, you declare that d of Li is the sum over all the arrows A of this expression, EI commutator of A star EI, where EI is something sometimes called the lazy path, is a path of length 0, starting at the vertex I and ending at the vertex I. So these things are just some formulas to cook up some graded algebra with some differential. You get some differential graded algebra, and then, which is called the Ginzburg DG algebra. And then you can consider the category of differential graded modules. And again, you put some appropriate finiteness condition. And this thing is what I will denote by C of Q and W. And by construction, this category will have this property of being Calabi-Yau of dimension 3, just something we forced in the definition. And you might ask about the relation between this new algebra and the old path algebra of the quiver. So actually, there is a simple relation between them. So if you think about what is the 0th degree cohomology of this Ginzburg-DG algebra, actually, it will simply be the path algebra of the quiver CQ divided by the relations coming from partial derivatives of W, so sometimes called the Jacobi algebra of the quiver with potential. So if there is no potential, it's just a path algebra of the quiver. And if there is some relations, if there is some potential, it's a path algebra with relations imposed by the partial derivatives of the potential. And it follows from this fact that inside this triangulated category or DG category, there will be some natural heart, a natural abelian category sitting inside it, which is simply the category of modules over this Jacobi algebra. So for example, if W equal to 0, it's simply the ordinary category of ordinary quiver representations sitting as an abelian category inside this bigger Calabi-3 triangulated category. And so later, when we'll discuss Donaldson-Thomas invariants of quivers, you can phrase everything in terms of ordinary quiver representations, and you never see anything looking like Calabi-3. But the reason it's related to this more general Calabi-3 story I will be discussing is essentially this construction. That this ordinary category of quiver representations, you can view it as being inside a bigger triangulated category, which are naturally a Calabi structure of dimension 3.
I'm sorry, what's the graded object in your DG algebra?
Sorry?
What's the graded object in the DG algebra?
So the DG algebra, it is this path algebra. And so a path is a combination of arrow. And every arrow has a grading. So every element in this algebra has a grading. So there is a graded, so there's a grading there. And you can check the differential should be compatible with this grading.
So for example, what about the degree 3?
Sorry?
The degree, for example, the degree 3 vector space. So what shall these look like?
If you compare the degree 1, degree 2, and degree 3.
Yeah. You have degree 0, degree 1, and degree 2. So about
Yeah, that's why they're like generators, they're like the arrows, and then you need to compose these arrows to get more general elements. Okay. So at this point, the main thing to remember is just these three main class of examples of Calabi categories. Is a derived category of Calabi varieties, or Fukaya category of Calabi symplectic manifolds. Or if you start with a quiver with potential, you can do this construction to get these categories which are Calabi of dimension 3, but which essentially are just made of quiver representations, but where the Calabi of 3 condition is kind of forced upon. Okay, so there are the three main classes of examples. And there are some non-obvious relations between these examples. Sometimes you might care about some category which appears in two different ways amongst the examples. So for example, mirror symmetry will relate the first two classes of example. If you have X, an algebraic variety, a Calabi variety, and if it's mirror to a symplectic manifold Y, then it's essentially a statement of homological mirror symmetry that these two Calabi categories should be equivalent. And sometimes a category coming from geometry might have some alternative description as coming from a quiver with potential. Or sometimes you might start with a quiver with potential and realize that your category has a geometric interpretation. And there are many examples of this phenomenon. Here I'm describing only one, which will be useful for later, which is if X is a smooth toric Calabi threefold. So a toric Calabi threefold is necessarily non-compact. So X is non-compact, and in general, there are regular functions on it. And you can look at the affinization of X. You can look at H0 XOX, the ring of regular function on X. and look at spec of that, you get some affine singular toric variety that are denoted by x scan, and there is a natural map from x to this x scan. And in this case, you can think of the derived category of current sheaves on X, which are set theoretically supported on the fiber of this map over the origin. So this affine singular toric variety will have a unique torus fixed point that are denoted by 0. And this map contracts a bunch of curves and surfaces to this point. And you can look at sheaves on X, which are set theoretically supported on these compact curves and surfaces, so that you get a proper category. And in this setup, it is known, there is a long story developed by many people, that there is a recipe to cook up a quiver with potential, Q and W, so that this category is equivalent to this Calabi-Yau 3 category attached to the quiver with potential. And here are some famous like example that if X is just C3, so C3 is an example. It's maybe the simplest possible toric Calabi-Yau 3-fold. And the derived and this category I was describing, so current sheaves on X, is equivalent to the category of a quiver with potential, where Q is a quiver consisting of a single vertex with 3 loops x, y, z, and the potential W equal x, y, z. And so to come back maybe to this question about this properness condition, so if you think about this example and this finiteness condition, geometrically it reduces your category of sheaves on C3 to sheaves which are set theoretically supported on the origin on 0. And this thing will have finite dimensional X and Hom groups, and this thing will be like kind of proper, essentially because the origin is proper inside C3. And here you can see maybe some, at least you can understand the connection between Q and W. If you think about the path algebra of Q, it will be like freely generated by X, Y, Z. And actually, I think my potential is actually wrong. So this potential is incorrect. I think the correct potential maybe look something like that. It should be a potential such that if you take the derivative with respect to x, it imposes a relation that y and z commute, that yz is equal to zy, and all possible cyclic commutations. So in this example, the Jacobi algebra would just be polynomials, commutative polynomials in 3 variable x, y, z, and reproduces the algebra of functions on C3. And here is a slightly more interesting example. If X is the Kp2, so local P2, so it's a total space of the canonical line bundle over the projective plane P2. So it is a line bundle O minus 3 over P2. If you look to the total space of this line bundle, it's a non-compact Calabi-Yau 3-fold, which has a natural toric description. And in this example, this diagram here, X to X scan is obtained by contracting P2 to a point inside this geometry. And then the category we're looking at are sheaves on this non-compact 3-fold, which are set theoretically supported on this compact P2. And then this category has a description in terms of a quiver with potential, where the quiver Q is represented here. It has 3 vertices. And in total, it has 9 arrows arranged like that. So it's a pair of 3 arrows that I call xi, x1, x2, x3, then yj, y1, y2, y3, and then zk, z1, z2, z3. And I wrote down the potential. So if you take any x and any y, any z, you can compose these 3 arrows, and you get some oriented cycle. And so you can take any of these cycles and take linear combinations of them. And here is a particular linear combinations with the coefficients are given by these tensors epsilon ijk, which are 0 if 2 of the indices coincide, and 1 or minus 1 depending on the parity of the permutation ijk. So it's a thing, it's a concrete thing with plus or minus 1 coefficients you can write down. So the main point, yeah.
So here in the first example, x, y, z are all of degree 0, right? Are all the regional quiver or not?
Yeah, that's right. This thing is the original quiver. So actually, in this example, there is something very special and maybe confusing happening, which is I think that if you start with a Jacobi algebra, it's already Calabi-Yau 3 on the nodes before you need to do anything. So I think if you do this kind of extra Ginzburg completion, it's like doing nothing if you think about it. Yeah, that's what I think so. Yes, this category will be just equal to that in these examples. Yeah.
And this diamond model equivalence that you stated in the previous slide?
Yes.
Is this still like a philosophy or is this a theorem?
Yeah, so I'm pretty sure the equivalence is like a theorem due to many, many people. And there's a very long story. If you want to search for some keywords, you can search for Dimer model. There is some combinatorial recipe starting from the combinatorial data of the toric Calabi-Yau 3 to cook up some quiver with potential, and then it's a theorem that they're equivalent. So there is a...
For the first example, the C3, that doesn't have, is that like with a group action, or how does this work? How do you get the, there's nothing compact in there.
Yeah, so here it's because here I look to the things which are supported on the fiber of this map. So actually in this map, the two are just the same. So just C3 going to C3, but then I have the origin in C3, so I'm restricting to sheaves which are like supported on 0 on the point, like set theoretically supported at the origin. And this thing is compact in this sense. Yeah, so as I said, the potential I wrote was probably incorrect, not correct. So probably it's still not correct, and you need to symmetrize this expression probably. Yeah. Yeah, thank you for pointing. So the main point of these examples is that in the later lectures, I will mainly focus on quivers with potentials because they have some purely combinatorial origin. But in some cases, they will tell us something interesting about something geometric. And at some point, we'll discuss such example. Yes?
In the first example, like you're saying it's equivalent to like CQW mod. Like where in CQW mod are you enforcing like the fact that it's supported at 0? Like X, Y, and 0.
Yeah, so this thing will come from this kind of finiteness condition I'm imposing. So this thing is a kind of, I'm imposing this kind of finiteness condition. And if you think about it, this finiteness condition will probably impose some kind of nilpotency condition on the matrix X, Y, and Z. And this thing will translate to the fact that your sheaves is like supported at the origin, like set theoretically. And like scheme theoretically, it will be some kind of sub-scheme, like a thickening of the origin inside C3.
It's just the dimension of the sum of HI.
Yeah, that's right. This kind of finiteness condition. Yeah, that's right. Okay, so we have these three main classes of examples. So the one coming from the geometry of sheaves, the one coming from Fourier category of symplectic manifolds, and the one coming from these quivers, possibly with a potential. So if you remember the first slide of this lecture, I was promising that we will be counting stable objects in such category. So now I need to say something about stability. And there are various notions of stability that you might consider, and I will recall some classical examples afterwards. Here I will simply go through the general definition due to Bridgeland of a stability condition on a triangulated category, which is probably the most general looking setup you might want to consider. So I will first go through the definition, and then I will explain on each of the examples we have been discussing what it is supposed to look like. Okay. So before talking about stability conditions on a triangulated or DG category, let me define what will be a stability function on an abelian category. So if A is an abelian category, a stability function, or sometimes called the central charge, which is a terminology coming from the theoretical physics literature. It's simply a group homomorphism Z from the quaternion group of A to C. So here K of A, or K0 of A is a quaternion group of A. It's a group freely generated by isomorphism classes of objects, where you quotient by the relation that if an object is in the middle of an exact sequence, then it becomes equal to the classes of the two objects on the two sides of the exact sequence. So K of A is always some abelian group, and every object in the category has a class in this group. And then you want to assign to every such a class a complex number. And the only restriction is that this complex number should live in the upper half plane. So if you think of C as being the complex plane, then you want all of these complex numbers to be of the form m e to the e pi phi, where m is positive. So you want to get non-zero numbers as long as you look at a non-zero class of a non-zero object. And the exponent phi, we'll call it the phase. You want this phase to be between 0 and 1. So you want the argument of your complex number to be between 0 and pi. So you want your number to be in the upper half plane. And you exclude 0 for your phase, and you include 1. So you exclude the positive real locus, but you include the negative real line. So a stability function is just a way to assign complex numbers to your objects. And you want this map to be like additive or linear. And the main point of having these complex numbers is that these complex numbers so have a phase. There is a natural argument. And because they all live in the upper half plane, there is a kind of well-defined phase between 0 and 1. And then you can use this phase to define a notion of stability or semi-stability. You can compare phases of objects and subobjects. So you can say that E is Z semi-stable if the phase of A is less or equal than phi of E for any A subobject of E in your abelian category A. And you say it's Z stable if you have strict inequality for every strict subrepresentation. And something you can check, which is a version of Schur's lemma, which will be important when we talk about moduli space, is that if E is stable, then its string of automorphism from E to E is simply the scalar multiples of the identity. And so the group of automorphisms of this object in the category is simply C star, or the non-zero multiple of the identity. So if you have an object which is stable for some Z, it's always like a simple object. This group of automorphism is as simple as possible, simply non-zero multiple of the identity. And here is a definition of, due to Bridgeland, of a stability condition on a triangulated category now. It's a data of two things, of a pair A, Z, where A is a nice abelian category sitting inside your triangulated category. So technically, it is the art of a bounded T structure. And Z is a stability function on this abelian category. And you ask for the following property. You want that Z satisfies an Ardern-Narasimhan property. So every object, non-zero object, in your abelian category should admit a filtration, increasing filtration, E0 inside E1, inside En, E. So this thing is inside the abelian category A. And you want the successive quotients, EI plus 1 over EI, to be all semi-stable of a given phase, phi I. And you want these phases to be strictly decreasing. Phi 1 should be bigger than phi 2, which would be bigger than phi n. So what this property is telling you is that any object in A, okay, might not be semi-stable, but is always made of semi-stable in the sense that there is this filtration with successive quotients are semi-stable. So this property is telling us in particular there are enough semi-stable to kind of reconstruct like any objects, essentially. So in practice, we'll not consider arbitrary stability conditions. We'll consider those with some kind of natural finiteness property. And in all the examples we'll be discussing, there will be a natural choice of a finitely generated group gamma equipped with a bilinear form, I will denote by omega on gamma, such that there exists a natural group homomorphism from the Grothendieck group of your category C to gamma. So it's a group homomorphism, some additive map, which intertwines between this omega on gamma and the natural bilinear form on the Grothendieck group given by the Euler form. So the Euler form is, if you have two objects E and F, you can consider the Euler characteristic between E and F, which by definition is an alternated sum of dimensions of X group between E and F. And because of our properness type assumptions, these X group are finite dimensional, so this thing makes sense. It's a bilinear form. And you can check it only depends on the class in the Grothendieck group. And I want my form omega to satisfy this property, that omega between the images of the classes of E and F by this map reproduces the Euler form. And then I will consider all possible stability conditions which have the property that this function z factors through gamma. Okay, so if you take a random category, K0 of C might be a very big group. It does not have to be finitely generated. But in all the examples we'll care about, there will be a natural finitely generated group gamma, and then we restrict to the z which factors through this finitely generated gamma. And there is an extra technical condition which will be relevant later, this which satisfies the so-called support property, which tells you that if you pick a norm on the real vector space gamma tensor R, there should exist a positive constant C such that the absolute value of the norm, absolute value of the complex number z of E should be greater or equal than C times the norm of E. And so if you think about what this thing is telling you that if you have a control on this complex number z of E, then you get a kind of control on the classes of the object E. In particular, if you have a bound on the norm on the modulus of the complex number z of E, you get a bound on the norm of E. And if you think of object in E having classes in this lattice gamma, it means you restrict your lattice to a ball of a given radius. In particular, there will be finitely many classes inside this ball. So if you bound Z, there will be finitely many classes gamma of semi-stable objects you might consider. So what is important is this restriction is only for E which is semi-stable. Else it will not actually make sense to impose this condition, but you impose it for E being semi-stable.
So it's kind of boundedness. So the support property implies some kind of boundedness.
Yeah, that's why it's some kind of.
Because what you said is satisfied in the case of stability for pure representations, no?
Yes, that's right. Yeah, that's right. Yeah, so it's some kind of boundedness for the essentially for the stability function. So for example, if you look, what it is telling you, if you think as some kind of picture in this upper half plane, and if you look at all possible semi-stable objects in your category, and if you think what this complex number looks like, then if you look at like bigger and bigger classes in your lattice of classes, this number should become bigger and bigger. So if you look at a bounded domain in this upper half plane, you should see only like finitely many z of E. And hopefully at the end of the day, we will see a concrete place where we'll use this fact when discussing the wall crossing formula at the very end. And then we have this theorem of Bridgeland telling us that this kind of set of all possible stability conditions satisfying this kind of two finiteness properties which factors through this lattice gamma and which satisfies this support property. This set actually has a natural structure of a finite dimensional complex manifold. And actually the complex structure can be characterized by the requirement that if you fix an object E in your category, or it will be enough to fix a class of an object E in gamma, then there is a natural function on the set of stability, which you have a stability AZ, and you look at the complex number that Z assigns to the object E. So for every object, or every class of object, there's a function ZE from the space of stability to complex numbers. And the claim is that there is a natural way to put a complex structure so that all these functions are holomorphic. So this result is conceptually important because it means that it makes sense, in particular, to move in a continuous way in the space of stability conditions. This space of stability is not some random sets, but actually it has a natural, it's a complex manifold, but it is in particular a topological manifold. It's in particular a topological space, and you can move in a continuous way in this space. And the whole wall crossing story we'll arrive to later will be about what happens when you move inside this space. So I will just end this first hour by discussing some examples of stability. So here is a most classical example, which is C is a derived category of current sheaves on a smooth projective curve X. Then there is an obvious T structure, obvious art, the obvious abelian category sitting inside, which is the category of current sheaves. So we take A equals the category of current sheaves. And you can take Z, the map from the Grothendieck group of X to C, which assigned to every current sheaf E, minus its degree plus I times its rank. And you can check that this thing satisfies the required properties. So why is it always in the upper half plane? So first of all, the rank of a sheaf is always non-negative, so it's always greater or equal than 0. So which look like the upper half plane. The only thing you need to worry about is could it be in the positive real axis? So if you're on the real axis, it means the rank is 0. But then it means your sheaf is the structure sheaf of a 0-dimensional subscheme. It's just supported at a bunch of points. And then its degree is the length of this subscheme. So this degree, in this case, is necessarily positive. And so minus the degree is negative. So actually, this real number will be on the negative line and not on the positive. So this thing satisfies the requirement for a stability function. And you can check that this pair AZ satisfies all what we want to be called the Bridgian stability condition. And if you think about what stable means in this context, you recover the usual notion of stability, going back at least to Mumford for sheaves on the curves, for which you compare the slope of the bundle. So you compare the degree divided by the rank. For a quiver with potential, you can define stability conditions in a way which is as easy as for current sheaves on a smooth projective curves. If I take this category CQW, which is this Calabi category of dimension 3 we attach to a quiver, as we mentioned, there is natural art inside, given by the modules over this Jacobi algebra, which for W equals 0 are just ordinary quiver representations. And in this example, K0 of the category is just the lattice Z to the power of the number of vertices. So it's already finitely generated to start with, so we'll just take gamma to be that. And then it's also very easy to cook up a central charge. You just pick for every vertex Zi a complex number in this upper half plane. And then there's an obvious map from gamma to C, which sends a dimension vector Ni to the sum over I, Ni, Zi. So here maybe there is something skipped previously, I should mention here. So how to think of this gamma of z to the power the number of vertices. So if you have an object in the art, if you have a query representation, it's a bunch of vector spaces living over the vertices. And all these vector spaces are finite dimensional. So you can look at the collection of dimensions of these vector spaces. You get a vector of integers, which is called the dimension of the query representations. And this gamma, this z to the power of the number of vertices, is a space of all possible query representations. So here, this z simply take a dimension vector, ni, and send it to the linear combination ni zi. And because all the ni are non-negative, because they are dimensions, if the object, then you get this condition. And so you can easily check that this A with Z is an example of a Bridger stability condition of this category. And on the abelian part, it reduces to an older and classical notion of stability for quiver representation called King's stability. And I will come back much more about this example tomorrow.
Can I go back to one?
Yes.
So K0C is exactly gamma because you are considering the nilpotent representations, right? Somehow.
Yeah, that's right. I think so. Yeah, that's right.
You need to assume Q has no oriented cycles for that to be true. Otherwise, you just have a surjection onto Z to the number of vertices.
Oh yes, you are saying maybe it's not equal, but there is only a map.
Yeah, so if Q
Yeah.
has no oriented cycles, then they're equal. If Q has an oriented cycle, then there's a surjection onto this.
But the fact that it's nilpotent implies the equality? Is that
Oh yeah,
all
we can
problem?
affect the opposing representations.
I mean, because, for example, if there is no oriented cycle, then there is kind of no condition, and then I can take any. I could take.
If you have an oriented cycle, then you have simple representations which are not non-latent.
Yeah, that's right. So it could be that in general there is only a map. And but yeah, in the previous definition, I was only using a map, so it's not, yeah. Thank you for pointing out. Yeah.
And the support property is always satisfied for any choice of xi. This is what is under the carpet here.
Yeah, yes, that's right. That's right. It will be as long if you take a z defined that way, then it will be satisfied. And of course, this thing is only an example. You might ask, are there other stability conditions? And in general, there will be, but this thing is a particular way to construct ones, and they will satisfy all the nice properties. Actually, I think maybe stopping there is a good point, because afterwards I will talk about examples involving some geometry, which will be slightly more involved. And so maybe it's good to stop here, and I will start again with geometry afterwards. Thank you.
Any other question or comment?
I just wondered, like, if you look at the King's stability conditions for focus, so you just need to assign which vertex you number. But how does this spatial stability compare to the Christian spaces, and how they interact?
Yeah, that's right. So in general, it's yeah, that's right. So this thing like define a part of the Bridgerian space, and you can ask what is globally the Bridgerian space. And this thing in general, it's a very difficult question. So it's only known in a few examples, and definitely, typically there will be stability conditions which are not of this form. For example, here the art is given by the standard art, but maybe there are other Bridgerian stability conditions for which the art is different. And yeah, so probably later I will come back to, maybe not today, but later to this example. So for example, on this category, there are ways to define Bridgerian stability conditions starting from the geometric point of view, which are different from the kind of obvious one we discussed on the quiver representations. And I think there are very few quivers for which we know the full story, but for most of them, I think we don't know actually what the full space looks like.
When you say different, means that they live in a different chamber in the space of stability condition? Or what do you mean by different?
Yeah, I mean, like for example, the art is different. The abelian category is different. But somehow they will be connected. Like, for example, they're in the same connected component of the space. So you can continuously go from one to the other, but they are not equivalent with respect to whichever natural equivalence you might think about.
This is for the known cases that you say?
Sorry?
This is for the known cases that you say, of where we know the stability manifold? Like,
yeah, that's right. So probably the stability manifold is probably known for the like AN quiver. So just the AN linking graph. And then probably in this case there is a non-global description.
in that case,
But
all of them king stability conditions?
sorry?
And in the AN case, are they all king stability conditions?
Yeah, I would have to. My guess is that like up to a natural equivalence. I think yes, but maybe you need to be careful. I will. Yeah.
Any other question? Yeah, please.
The definition of the central charge matrix is upwarding. There is also S double Z actually. Is there some kind of use of it before that?
Yeah, that's what someone sees. Yeah, let me. It was here. Yeah, that's what. So actually. Yeah, so actually on the upper half plane, because here the integrality lattice does not really play a role. So actually there is really an action of SL to R. And so it's true that this action on the upper half plane, for example, induces an action of actually the universal cover of SL to R, or maybe the universal cover of GL2 plus R, is acting on the Bridgian space of representations. And sometimes this action is useful. If like two stability conditions are related by these actions, maybe you can decide they look the same. And so maybe you might decide to take the quotient by this action to get some more honest thing. So yes, this action is somewhere in the background and sometimes useful.
Any further question?
So if I may ask about the Fukaya category,
Yeah.
just to get a sense of how it looks like. So is it easy to describe like what X should be and what the points should look like?
Yeah, so I think in general it's, yeah, I mean, describing the Fukaya category is a non-trivial business. So, I mean, in first approximation, the kind of toy model to think about is that if you have L1 and L2, two Lagrangian submanifolds, and if they intersect transversally, let's say infinitely many points, then the home space between the two is constructed from a complex with generators as the intersection points between these two Lagrangians. And then there will be some differential having to do with counting holomorphic disk with boundary on these Lagrangians. And then depending what this disk look like, you might get a simple or complicated answer. But like if you are lucky, if there is no disk at all, for example, the dimension of your home space would just be the number of intersection points between your two Lagrangians. But in general, it's a very non-trivial story, I mean, business to figure out.